Can you see my screen?
Yes, sir.
All right. So today's all right. So the question I asked is the following. So in analysis 3 course, you have seen function, right? A function, let's say, from a domain omega, domain in Rn to, let's say, Rm, a differentiable function. Now, what is the domain of df at A, right? So what is the domain? Let's say A is in omega.
Sir, it's a linear map from Rn to Rm, so it's the whole of Rn.
Whole of Rn. Why?
Because it's a linear map.
True. But whether is this whole of Rn coming from omega?
No, sir, it is something else.
Yeah. So it is actually mapped from the tangent space of omega to Rm. Tangent space of Rm. And that's what is in the hindsight. All right. So this TDFA is a map from Rn to Rm, linear, right? So the question is, I mean, you know linear, but the question is, where does this Rn coming from omega? Well, yeah. So that is coming from the tangent space of omega. So what?
Sir, could you scroll up?
Yeah. Any question? So why is the domain of DFA Rn? Because of course it's a linear map. True. But the point is here, this Rn, or rather, better question would be, yeah. The better question would be, where does this Rn coming from omega? So the point is that, so answer, so this Rn is the tangent space of omega at point A, at the point A. So that's how it is. So we and of course now we have given this definition. This is very easy because f is a function, so dfa we go to Rn, we show that Rn, that is a number, and it's a, sorry, in R go to R, and we show derivative is evaluated at a point is a number that can be seen as a linear map. Hence, we can generalize this way. So that was the idea of explanation in analysis 3 course. But now the point is this one, there is a conceptual thing on that one. Apart from just a generalization of Rn, it becomes actually this derivative map is map from tangent space, one tangent space to the other. So one can think of that way as well. So at each point of omega, you attach a whole of Rn, which becomes tangent space. All right, tangent space of omega. Now, well, that is quite good, but how does it become the tangent space? Let's look at it in Rn. So the concept of tangent space. So what did we do last time? We looked at what did we do? What did we do? We defined something called derivation. Did we define derivation? Derivation? Not yet, right? So we corresponding to vector. So last time we have seen that given a differentiable function, if, well, I'm not mentioning at the domain, but it is actually true in a neighborhood of a point, that is good enough. On a neighborhood of point P. So given such a function, for each vector V in Rn, we can correspond to summation. So V in Rn, V is V1, V2, Vn, summation Vj del by del Xj, right? Is it fine? You don't need a function here. So it is, well, this is the point. So dvf, the directional derivative, which can be looked at. So this is actually equal, right, at P, at the point P. Well, this is dv is already at a point P. All right, this we have seen, isn't it? Is this conceptually clear? Is this clear, first of all? So corresponding to a vector, you have the directional derivative along that, and that can be written as in this form, right? This can be written as in this form. Is this fine? So therefore, we can actually write, we can write dv as summation vj del by del xj, j from 1 to n. This we can write. All right. So vector corresponding to a vector, you have directional derivative dv, and that can be thought of this way, right? All right. So remember this one. This is very important. So this is very important. This is kind of the fundamental to define tangent space. So before going further, we need to define something called germ of functions. Have you heard the term germ? Germ of functions? Well, so here, what is the idea? Idea is as follows. So you have a domain, let's say omega in Rn. That's not important actually. Consider a point, this is important. Consider a point P and look at a function in some neighborhood. So call this U and f is suppose f is defined from U to R, right? C infinity. You can consider another neighborhood, let's say V. So G might be defined in V to R, C infinity. You can consider another one, call it W. So H defined from W to R, C infinity. We want to combine all these functions, but neighborhoods are varying, right? And that is the reason germ of function, the concept of germ is coming into the play. All right. So which is an equivalence class of functions. So consider the set as follows. Consider script A. U, comma, F, where U is a neighborhood of P and F from U to R, C infinity. Just like this. Yeah. Now we give a relation, or define a relation on script A, on script A as follows. U comma F is related to V comma G if there exists a neighborhood U tilde of P such that U tilde lying in U intersection V and F restricted to U tilde is equal to G restricted to U tilde. Is the relation clear? Is the relation clear? Any question here? So you consider all such functions, but neighborhood, the function where it is defined is varying. So you combine the neighborhood and the function. All right? Now a neighborhood combined with that function may be related to another such pair. When? Precisely when there exists a neighborhood where those two functions actually have same values in whole neighborhood. Yeah? Is it an equivalence relation?
So we have fixed the point P from the start, right?
Yes. Yes. So we can denote this AP. Yeah. So relation on AP. So P is fixed from the very beginning. So is it an equivalence relation?
Is there a condition that U tilde has to be non-empty?
Yeah. So P is there, na?
Oh yeah.
Yeah, it's automatically non-empty. Yeah, so check. This is very simple to check. This is an equivalence relation. Right? So C infinity P, let's say, yeah, Rn, because you have taken this P, oh yeah, P in omega. So P in omega in Rn. So that is fixed. So here, this is the equivalence classes of AP under this. So this is called the set of germs of functions at P. All right, make sense? The point is, it is locally defined, first of all. So remark two different function of two functions having the same germ at P may not be equal globally. You have seen examples, right? For example, you look at fx to be 1 by 1 minus x on where r minus the point 1. Yeah, this is infinity function. And consider gx summation x power n from 0 to infinity. So gx is defined on where?
Open minus 1.
Right. So are these two equal? Are these two functions equal?
Yes, sir, on open minus 1.
Right. So fx is equal to gx on minus 1 to 1, but g is not defined outside, right? Outside minus 1 to 1. But this function is defined. So f is defined on r minus 1. So though they have the same expression around 0, let's say minus 1 to 1, but outside they are not equal. So in complex analysis also you can see this function fz equal to 1 over 1 minus z and gz to be function z to the power n. Right? Any question? Yeah, now why do we need Germ of functions? Because of the following reason we did here, that corresponding to corresponding to each v we have certain things like this, and this one acts on function, C infinity function, and that is why so we look at Germ of function, and this will act over there. All right. So what we would like to show now is, now we define derivation at a point. So what is the derivation at a point? So fix a point, fix a point P in Rn. Omega is not necessary at this point, right? Now let V be a vector in Rn, right? Zero vector gives you zero, definitely, but corresponding to dv, you can dv would act on C infinity P Rn to R, right? So dvp, so V is V1, V2, Vn. So dvf, so let's take a germ f. So f defined on some neighborhood u, so derivative is defined. Once there is a neighborhood where a function is defined, C infinity function is defined, you can take derivative. And now dvf will look like summation vj del f by del xj, j from 1 to n. All right. So this is the derivative. This is the directional derivative. The directional derivative. In the direction v. All right. Yeah. Now what it satisfies? Let us fix the some properties. So properties. So such a directional derivative have the following properties. One, dv is r linear. So linear over the said real number. All right. So the collection of germs of function forms a vector space, right? So here I put a small note: C infinity P power n, or sometimes I'll write C infinity P if Rn is very clear from the context. It's a vector space, right? Does it have a multiplication structure also? Is it a ring also? Yeah? Is it a ring? Come on. Should answer these things. So what you should be thinking about, I mean, thinking of germs of a function is nothing but a function defined on an arbitrary neighborhood of the point V. That's it. And which are, I mean, the germs will be actually all the function will be same, which are equal in one neighborhood. C infinity Rn is also a ring, right? So you have multiplication structure as well. So it's an algebra. All right. So this two combine these two forms the C infinity P Rn forms an algebra. All right. So second property is the Leavening rule, right? That is that you know from the very beginning. The dv fg, right? This is dv f times gp. So here remember this one. This is not del f by del xj at a function. This is evaluated at the point p. This is important. Did I write that before? If I did not write, then I should. Yeah, so this is at the point P. So this del f by del xj, we are not allowing this to vary over x. It is evaluated at the point P. This is dvf times g is dvf times gp, and this fp dvg dvg is already evaluated to p. It gives a real number, right? Derivation is such that, yeah. So here it is. So it gives a real number. So it gives a real number. So if you do not evaluate at p, it will not give a number. You will get a function in a neighborhood of p. That's what we don't want. Any question here? All right. So you have. Let me give one exercise. It's very simple. Exercise. So that if so the point is here, before going into the exercise, let me give a remark. So we know, or we define the tangent space of Rn is Rn itself, which is collection of all vectors. So that would imply for a domain omega in Rn, Tp Rn, Tp omega, P in omega is whole of Rn. collection of all vectors. This is by definition. Now, if you consider a vector from TP Rn or TP omega, whatever you want, and this corresponds to summation Vj del by del xj at P, right? J from 1 to n.
Sir,
Right? So
why
this
did you
is
put TP omega? I thought it had nothing to do with omega.
because, yeah, it has nothing to do with omega. So it is true for any omega. So my point is so that you don't confuse that whenever you want to define tangent space, you need to have whole of Rn. That is not needed. So that's why I wrote this line. This line is kind of redundant actually. So this omega is any open set you take will have these things. So, but the point is that you do not need whole Rn to define the tangent space. That is the point. Yeah.
Yes, sir.
Okay. So here, if you for Rn we have the tangent space Rn itself. So you have every vector. So corresponding to a vector, you have directional derivative, and that looks like this, right? So this. So did I what did I define here? So right. So this one. So this one having two properties. So now we'll define the following. Definition. A derivation d at a point p in Rn is an R linear map d from C infinity p Rn to R such that d of f times g is df times gp plus fp dg. All right. So d is not derivative. D is the derivation. All right. So here call this script tprn is collection of all derivations at p. Now this one gives a map from the tangent space to the derivation. So for Rn, I mean, defining tangent space was very easy because you just consider Rn itself, collection of all vectors. But for general surface or general manifold, it is you don't have a vector space right at the beginning. So you don't know what the things, and that is why we are just extracting the properties of derivation, properties of the directional derivative, and look at the tangent space in this fashion. So define map phi from TPRN to d script d dprn by p of v is equal to summation vj del by del xj. All right. Yeah. Makes sense. So exercise D if
Sir, could you show the last page? I mean, left side.
yeah, is this fine? So this is Leibniz rule. So first properties are as follows. This is our linear map, and this satisfies this property. So this is Leibniz rule. So R linearity and Leibniz rule. All right. Any question? Now next exercise is if D is a derivation or point derivation at P, then D of constant function is 0 for all constant function C. This is very easy exercise, so I'm not going to do it. So use Leibniz rule and you'll get it. So a theorem, the map phi from TPRN to DPRN is an isomorphism. So this is very important because now we can abstractify the tangent space, and the derivation part we can move to any manifold, any smooth manifold. You do not need the structure of Rn or an open subset of Rn. You do not need that. So for the derivations, one can define anywhere in any manifold. So with the notion of smooth functions are there, you can define derivation.
Sir,
Yes.
what is derivative?
What is derivative? Yeah, that's what we are up to, right? This is the derivation. Derivation is a map. So that uh, corresponds to the directional derivative. So what is the derivative of a map from a manifold to other manifold? We are going towards that. So for that we need the notion of tangent space. So in our case, notion of tangent space in Rn, it's very clear collection of all vectors. So it gives you Rn again. But for a manifold, we do not know, so we want to define it. So this theorem gives you an isomorphism between TPRN to DPRN. So before proving the theorem, so before going into the proof, so maybe note del by del xj at P is a derivation, right? And del by del xj at P applied on a function, let's say xk. So what is it? Delta jk, right? Yeah, which is equal to 1 when j equal to k and 0 when j not equal to k. All right. Is this clear? Well, let's look at now the isomorphism part. So injectivity proof. Suppose the derivation dv is 0, right? For so for suppose for b belongs to pprn, dv is 0. We want to show b is 0. To show b is identically 0. So dv acting on the function f, right, is summation vj. This is by definition del f by del xj at p, right? J from 1 to n. Now take, let f x equal to xj, right? Or let's say xk. dvf is nothing but summation j equal to 1 to n vj del xk by del xj at p, which is vk. So, and this was 0, right? So this implies vk is 0 for all k 1 to n. So this implies v is 0, right? Simple proof. So in this course, the proofs are basically will be very simple. Once you understand the definitions, the proofs are very simple. Nothing much of this. So the definitions are most important to understand what is going on and the calculation in local coordinate. Once you can do it, other things are easy. So how to show subjectivity? How will you show subjectivity? So given T is a map from C infinity P Rn to R derivation. To show there exists a vector V in Rn such that D is equal to dV, right? We need to find V. How to find this V? So let F be a, well, U comma F be a germ of functions at P. Without loss of generality, shrinking, we can take U to be a ball centered at P with some positive radius. Of course, that is true because it's an open set. All right. Now, what you need to do is you need to apply Taylor's theorem first, right? So apply Taylor's theorem on it. Since f is C infinity, apply, we can apply Taylor's theorem. theorem. So this part you have not seen. If you have not seen it, it is an exercise. So there exist the infinity functions gj, j from 1 to n, such that fx equal to fp plus summation j from 1 to n xj minus pj gjx. So this is by Taylor's theorem. So if you have not seen it, this is an exercise. This is by Taylor's theorem. All right. Once you can expression in this way, then you apply D. So yeah, D of f at p, of course. D of f at well, you don't define at p. So D is already a derivation at p. So D of fp, D is R linear plus here this is R linear. So j equal to 1 to n comes out. D of xj minus pj gjx. All right. Now this one is 0, right? So we need to look at this.
Sir, could you show the last page? I couldn't write.
Okay. Yeah, is this fine?
Yes, sir. Now you continue.
All right. So now what is df is summation j from 1 to n d of xj minus pj gj. All right. Now here we use Leavening rule. So that gives us j from 1 to n d of xj minus pj into gjp plus pj minus pj d of gj. All right. Now this one is again 0, right? So here j equal to 1 to n. This is d of xj minus d of pj, right? gjp, right? Well, there is a mistake here, so I need to specify what it is. So here there exists a function gj that is true such that this and there are one more property. Gj at p is del f by del xj at p. All right. So this is important. At p, it is just the derivative, and that should happen, right? So if you look at this expression in Taylor series, so that part is important because uh, this is ap and then this xj minus pj times del f by del xj that is coming in. That is the things that comes, and then there is higher order term. So gj actually combines with that del f by del xj at p plus higher order terms. All right. So this part is also important.
Sir,
Yes.
isn't that automatic? Because if we define, if f is equal to that in the interval, and
Yeah.
if I take partial derivative over there, won't this come out?
Of course. That is true.
So do we have to mention that explicitly?
Oh no. See, you have del f by del xj is at p. That is true. I mean, if you once you have this one, yeah. So this comes as automatic. Once you have this one, then del f by del xj at p is nothing but this one. That is true. That is true. Yeah. So you do not need to mention automatically. Yeah. So that part. Yeah. So this part is automatic. Yeah, from the expression. From the expression. That is true. Expression. Yeah, but this part is an important observation. This is needed here now. So here this one we would need it. So summation j equal to 1 to n dxj, and this is 0. So gjp. So this is nothing but j from 1 to n dxj del f by del xj at p. So what is the vector? Yeah. So d corresponds to dv. So what is the vector v? Where v is, or rather, I should write d equal to dv. Where? So what is v?
So d of xj components.
Right. So this is d of x1, d of x2, d of xn. This is the vector. Hence, phi is surjective. And so all this implies phi is an isomorphism. All right. So we'll take a break here for some time. Let's say 15 minutes. Then we'll come back.